As engineers, the academics and the Faculty of Engineering are naturally inclined to a continuous improvement ethic. Initial institutional program renewal workshops saw the team identifying specific stumbling blocks in our programs, as well as envisaging our mission to cultivate graduates that develop innovative and sustainable solutions to society's complex engineering problems. The question of how we develop such graduates has continued to be refined and investigated across a number of faculty initiatives. Under the leadership of the Vice Deans teaching since 2017, the faculty has adopted a holistic approach to program renewal in order to address 4 specific strategic themes. We make use of a range of opportunities, sources of funding, and staff events under the umbrella of our Recommended Engineering Education Practices project, which we call REAP. Now, REAP is our faculty community of practice through which we investigate, research, implement, and share practices for inclusion in our faculty-endorsed REAP guidelines, a living document constantly being refined. All our work is aligned not only to fundamental curriculum principles across the student pipeline landscape, but also aligned to scholarly informed models. As educators, we're interested in developing the whole person, which is our higher education mandate, the development of knowledge, skills, and citizenship. Now, this means that our cognitive, affective, and psychomotor educational objectives should be aligned to epistemological, ontological, and praxis curriculum dimensions. To enable access to such a holistic curriculum and learning activities, we need to provide cognitive, affective, and systemic support using knowledge of appropriate content, pedagogy, and technologies. Now, using this holistic CAS model enables us to separate out different layers. For example, to analyze our curricula or specific learning activities, so that we can check that we're working holistically. The CAS framework is the umbrella for our REAP initiatives, which are covered by Impact Evaluation Ethics Clearance. This means our community of practice can formally engage in innovation and research in their teaching and learning. We have an active community of practice publication track record in engineering education, which of course is part of our ethic for continuous professional development in the faculty. Now, we're going to share a number of our initiatives with you, starting with our overarching CAS model. As a result of COVID-era teaching and learning, we saw a need to better address our undergraduate and postgraduate student affective needs, as well as to improve our systemic support by analyzing how our students are using and experiencing our systems. There is a concerted effort to bridge gaps in the foundation and mathematical sciences by providing informative and developmental cognitive support through online quiz banks and self-study learning platforms, for example. We'll take a look at specific examples in a moment. Now, if we take the student pipeline approach and the key curriculum principles as summarized by the Council on Higher Education, we need to ensure 4 things. Foundation support to bridge knowledge gaps from school. Explicit scaffolding of the epistemic transitions from the natural and mathematical sciences through the engineering sciences to application, design, and management. The 3rd principle is the need for curriculum enrichment through key literacies. And the 4th principle is the need to enable greater breadth of exposure in order to produce graduates for the contemporary world. Here we have these 4 curriculum principles in relation to an idealized cumulative learning wave over time. In other words, connecting abstract concepts to concrete contexts through different forms of application using different tools. Now, the scope of our work plays out across the engineering student pipeline. At the foundation level, You've already seen we have a number of initiatives such as the Unit Conversions Estimations Quiz Bank, developed over years by a team of academics in chemical engineering. As a result of program analyses, we've paid increasing attention to enabling what we call epistemic transitions from one kind of knowledge to another, from natural and mathematical sciences into the engineering sciences, as these represent our key bottleneck modules. In order to provide program enhancement that speaks to the curriculum from the world of work, we've also conducted a number of alumni surveys. Now, a number of our UCDG 2021 projects have been informed and enriched by our experience of emergency and subsequently augmented remote teaching, learning and assessment, highlighting our faculty focus on establishing REAP principles across our programs, enabling improved student engagement, developing formative assessment strategies and practical engagement by harnessing appropriate technologies. Our faculty-wide academic stress management survey revealed a need for more holistic student support. We are developing peer learning and mentorship initiatives and have implemented a tools for academic success module for our students, which helps them identify learning and emotional support resources, for example. Our faculty-wide SWOT analysis revealed the potential of recent remote learning systems for better scaffolded, formative and peer learning initiatives. The faculty is currently engaged in a review of its extended degree program and mainstream students. This review has helped us to identify learning challenges for all our students, particularly the need to address holistic inclusion of all 4 curriculum principles. Building on previous alumni surveys in the faculty, Process Engineering has conducted an alumni survey which has given us very important insights. The faculty plans to extend this study across all departments.
Our first case study is a first-year chemistry course for all engineering disciplines with around 1,000 students. There isn't time to revise the chemistry fundamentals, so a group of lecturers has developed a randomized online quiz bank. The activity was designed to be a low-stakes formative assessment, allowing the students to retake the tests in order to improve their marks and, of course, to learn. Questions in the database are designed to allow the students to surf down the wave, pulling through the conceptual through to the contextual through a set of progressive questions. Questions range from pure science, foundational, conceptual or theory-based questions that may be somewhat abstract to the student and move into the application of theoretical concepts in scenarios where there's a clear formulaic or mathematical procedure that can be applied. Finally, the students move to questions with less clearly defined answers, but that are contextually familiar to them, where they would be required to use some sort of engineering judgment. In our second case study, we start at the bottom of the wave with a flipped classroom case study assignment for a second-year material science course for mechanical, mechatronic and industrial engineering students. The challenge in this syllabus is to avoid siloed learning in the face of the broad and dense syllabus. Lecturers use a case study of failure analysis in order to pull various theoretical concepts and procedural analysis techniques together in a real-world application. Again, this is designed as a low-stakes assessment in the form of a reading assignment, a walkthrough video that directs students back to the textbook chapters to help them connect the dots, and a multiple attempts online comprehension quiz with formative feedback between the attempts in order for students to check that they are getting it. The student is taken on a job shadow journey with a consulting engineer, climbing back up the wave by starting with a contextual real-world engineering problem. A vehicle wheel axis has failed and you as an engineer need to determine why. Various material and mechanical tests are used in order to determine the material and mechanical properties of the axle, and then the properties are linked back to the expected behavior from a theoretical perspective. The student is then guided into interpreting the results in order to determine the reason for failure. Now we look at moving up and down the wave, integrating concepts and applications and contextual situations. In this case study, a third-year transport engineering course for civil engineers is used. Students are assigned a road design project where they work in small groups to find an appropriate local site where they can apply road elevation concepts to create a particular road design. This case study is designed to use elements of experiential learning, peer engagement, and teamwork to simulate a real-world engineering application, including tasking them with the use of software and translating technical information into a readable report. The students snakeboard up and down the wave to integrate the know, be, do elements of learning engineering. They start with the conceptual and look for a contextual scenario where the concepts can be applied. Then they apply the analysis and design principles and procedures to create their solution, and integrate these elements into a final design report where they have to use the road design software.